Dear friends, welcome to a lecture on ring theory. In this lecture, we shall study isomorphism of rings. In our earlier lecture, we have studied homomorphism of rings. I have written definition of isomorphism, which is a special kind of homomorphism. We shall see the definition and then we shall prove a lemma on it. The definition is a homomorphism of ring R into ring R dash or R prime is said to be an isomorphism if it is one-to-one mapping. So isomorphism between two rings is a mapping. So we have generally denoted the mapping between two rings as phi, and phi from R to R dash is isomorphism. Is isomorphism if it is homomorphism, or we can write it is if it is homomorphism that is necessary. And what are the two properties of homomorphism? We have seen earlier as phi of A plus B, structure preserving properties. You should refer the earlier lecture, which is lecture number 6 or homomorphisms. Phi of A plus B is equal to phi of A plus phi of B for AB belongs to R. And the second property is phi of A into B is phi of A into phi of B. And these are the two properties of homomorphism that must be first satisfied. And second is phi is 1-to-1. Phi is 1-1. Then this homomorphism phi is known as isomorphism. So this is the definition of isomorphism, a mapping which is homomorphism and 1-to-1. Next definition about two rings. When two rings are said to be isomorphic, if there is an isomorphism between two rings and which is also onto isomorphism must be there. And in this case we write two rings are isomorphic by this symbol. R is isomorphic with R dash with corresponding binary operation, with the respective binary operations plus and that is addition and multiplication, may be same or may be different for R and R dash. So if there is an isomorphism, two rings are said to be isomorphic. And now we shall prove this result as a lemma. Lemma generally is considered as a result which is prerequisite of a theorem. Lemmas are useful to prove a bigger result, which is a theorem. And this lemma is the homomorphism phi of R into R dash is an isomorphism if and only if I of phi, what is I of phi is kernel of phi is equal to 0. That is kernel phi, or in short we write like this: kernel phi contains only 0 element. So this is the meaning of the result, and this is a necessary and sufficient condition for homomorphism to become isomorphism. If kernel of homomorphism contains only 0 element, then 0 element of R, then that homomorphism becomes isomorphism, and vice versa. Now we shall prove the result, because the result has if and only if part. First we shall consider that phi is isomorphism, and then we shall prove the kernel of phi is equal to 0. So first let phi from R to R dash, we denote like this: phi from R to R dash be an isomorphism. Now what we have to prove is kernel of this phi. Earlier we have defined what is the meaning of kernel phi. Kernel phi, which is denoted by I of phi, is the set of all elements in R, the first ring, such that phi of A is equal to 0. You refer the earlier lecture, there we have defined kernel of phi. and that contains only 0 element, that is 0 is mapped to 0 here. And we shall consider let x belongs to kernel phi. Let x belongs to the element kernel phi, and that means x is in R. And what this implies, so this will imply by definition, if x is in kernel, then phi image of x is equal to 0. So this implies phi of x is 0. So this will imply phi of x is equal to 0. And but we have 0 is phi image of 0 is again 0. This 0 is in R dash. And this implies phi of x is equal to phi of 0. Since we have the result are in the lemma on homomorphism, that is phi image of 0 is equal to 0, 0 in R dash, this 0 is in R. And now see, this implies, so phi is isomorphism, and therefore phi is 1 to 1. And because the mapping is phi is 1 to 1, this phi of x is equal to phi of 0, their images are equal, implies their inverse images are equal. That is the definition of 1 to 1 mapping, and therefore this implies x is equal to 0. So that's what we have. If x is in kernel of phi, then x is 0, means kernel phi contains only 0 element. And this thus this shows that thus kernel of phi, which is I of phi, contains 0 element only. That is the first part of the result. If phi is isomorphism, then kernel phi is equal to 0. Now converse part we shall consider as second. Now conversely, let kernel phi is equal to 0. Let kernel phi, and that is I of phi, is equal to 0 or contains 0 element. Now what we have to prove is phi is isomorphism, and earlier given that phi is homomorphism. To prove it is isomorphism, we need only to prove it is 1 to 1. A 1 to 1 homomorphism becomes isomorphism. We have to prove phi is 1 to 1. We shall prove phi is 1 1, and for that let to prove 1 1, we shall have to prove the property considering two elements. Let x y belongs to R, and let and phi of x is equal to phi of y. We need to prove that x is equal to y. That is the definition for 1 to 1 mapping. Their images are equal, then their inverse images are equal. That is the condition for 1 to 1 mapping. So this further implies, we can consider this element on the left side, and that can be written as phi of x minus phi of y is equal to 0. Or this can be written as phi of x plus phi of negative y. This is the earlier lemma on homomorphism. Phi of negative y is equal to negative of phi of y, and therefore we can write like this, and this is equal to 0. So but this is because phi is homomorphism, this can be written as phi of x minus y, phi of x plus of minus y, or that is x minus y, and is equal to 0, since phi is homomorphism. And now what this shows, phi image of x minus y is 0, and that means x minus y must be in the kernel of phi. This implies x minus y belongs to kernel phi. But what is kernel phi? Kernel phi we have only 0, and that is equal to 0, contains single element 0. and therefore this x minus y must be equal to 0, and this implies x is equal to y. And what this proves? This proves that phi is 1 1. So therefore phi is 1 1. And because phi is homomorphism, phi becomes isomorphism, and thus phi is an isomorphism. So this proves the lemma, and thus the lemma provides us a necessary and sufficient condition for a homomorphism to become isomorphism. Only we need to prove kernel phi is 0, then it is isomorphism. So this is about the definition of isomorphism and a result on isomorphism. You see the difference in isomorphic rings. When a ring, two rings are said to be isomorphic, if the isomorphism is onto R dash, and that means these two rings will be isomorphic to each other. That is, R is isomorphic to R dash. See, R isomorphic to R dash if there exists phi, if there is a mapping phi which is homomorphism from R to R dash, which is first phi is that is homomorphism, then second is 1 1, and third is onto. If there exists 1 1 onto homomorphism, then the two rings are said to be isomorphic. Now, example of isomorphism, a simple example of isomorphism is identity map between two rings. So, examples of isomorphism. Let R and R prime be two rings. We define phi a mapping from R to R dash by phi of x. Actually, this example we have considered in homomorphism also, and that homomorphism is becoming isomorphism because it is 1 to 1 for all x belongs to R. Then this is an isomorphism. Then phi is a homomorphism, 1 to 1 homomorphism. Because it satisfies the structure preserving property, two properties, phi of x plus y is equal to phi of x plus phi of y, phi of x into y is equal to phi of x into phi of y, and this is 1 to 1 because you see the kernel of this, let see x belongs to, let x belongs to kernel phi, and then this implies phi of x is equal to 0. But what is the 0? 0 is the image of 0. So this is also equal to phi of 0. And now what this implies? This implies x is equal to 0, and therefore kernel phi is only 0, and therefore this implies kernel phi is 0. And see, because by the earlier lemma, if kernel phi contains only single element 0, then the mapping becomes isomorphism. It is one-to-one mapping, and that is isomorphism. So this is simple example of isomorphism. Another example of isomorphism can be considered as this one. So I shall write here. Second example, let R be a ring of R be the ring of integers. All integers with usual addition and multiplication. Further, let R dash be the set of all even integers. And we consider usual addition, and we define usual addition for R dash. Let R dash be under usual addition, under usual plus, and define multiplication R dash. We define multiplication differently in R dash, denoted by this symbol. This is not usual multiplication. We denote multiplication in R dash by this symbol asterisk, defined by A asterisk B is equal to AB divided by 2, for AB belongs to R dash and AB is usual product, usual multiplication of integers. Now see, this is the only difference. R is a set of, R is the ring with a ring of integers with usual addition and multiplication. R dash be set of all even integers, and R dash be under usual addition. Addition in R dash is usual, and multiplication in R dash is different. That is denoted by this symbol A star B or A asterisk B is equal to, and that is A into B divided by 2. This multiplication is usual multiplication of integers, and that means if you consider two even integers, say 4 and 8, then what will be this product? Multiplication in R dash, that is 4 into 8 divided by 2, and that will be 16. So this is the meaning of this multiplication, and under this with this multiplication, this R dash becomes a ring that you can check easily. This R dash, then we know R is ring with plus and dot. Then this R dash with usual addition and this special multiplication is a ring. This is a ring. You may verify the 8 axioms of ring, and for R dash plus, we have seen this example. It is a set of all even integers with usual addition and multiplication forms a ring. But here not usual, the multiplication is changed, and instead of usual multiplication it is defined like this, and that also forms a ring. So R dash with plus is an abelian group. This multiplication is closed because A and B are even integers. They divided by their product divided by 2 is also even integer, just we have seen, and therefore it is closed. And this multiplication is associative, and the multiplication this multiplication is distributive over addition. You may check these properties, and this is a ring. Now what now we define is an isomorphism between R and R dash. Define phi from r to r dash by phi of x is equal to 2x, and this x belongs to r, first set integers. So then we shall check whether this is an isomorphism and if it is 1 1 and onto. And you may see this is r, all integers, and this is r dash, even integers. So here if you consider the elements 0, then 1 2 3 etc., negative elements, but here the elements are 0 2 4 6, only even, and negative even integers are there. And how the mapping is defined, phi of x is equal to double of x, and therefore phi of 0 will be mapped to 0, 2 into 0. Phi of 1 will be mapped to 2, phi of 2 will be mapped to 4, and so on. So this is minus 1 into my 2, that this is the mapping defined. Now we shall prove this is an isomorphism and also onto isomorphism, and that means first we shall prove it is homomorphism. Then phi is first thing. We shall prove phi is homomorphism. What are the two properties of homomorphism we need? Let A and B, AB belongs to R, this ring, and we need to prove phi of A plus B is equal to phi of A plus phi of B. Structure preserving properties, two properties, one for addition, another for multiplication. By definition of phi, this is 2 times A plus B, and this can be written as 2A plus 2B. And what is 2A? That is phi of A. Again, by definition, 2x is phi of x, 2A is phi of A, 2B is phi of B, and this proves the first. Now second, and phi of A into B, this is equal to phi of A into B. I shall write here. Phi of AB. See, by definition it is 2 into AB, and we can write this as 2A 2B divided by 2. Check it, it is the same. And what will be this? This will be 2A, that is A star B, or 2A asterisk 2B. By this definition, A star B is equal to A into B divided by 2. Now this is 2A 2B divided by 2 will be 2A star 2B by the definition. You see, in place of A there is 2A, in place of B there is 2B, and it divided by 2. So therefore it is a product between 2A and 2B in R dash, in this. So here this is the ring with usual addition and asterisk multiplication. This is usual addition and usual multiplication. And what is this? This is 2A is phi of A by this definition, and asterisk phi of B. And this proves phi of AB is equal to phi A star phi B, and that preserves the structure, this dot and this is star, and thus phi is homomorphism. Now next is phi is 1 1. So that is second condition. Phi is 1 1. Now this is obvious and easy. So phi of x is equal to 2x. So what we shall consider is xy belongs to R, and phi of x is equal to phi of y, and we have to prove x is equal to y. So what this implies, phi of x is 2x, phi of y is 2y by the definition, and this implies x is equal to y. So therefore phi is 1 1. And now what remains is phi is onto. onto mapping is a mapping. Consider an element in the second set and then image set, and then or this codomain, and then we have to prove there exists inverse image for every element of this. Consider an element, let y belongs to r dash. An element in this we have considered as y, and we have to prove there exists an x element here which is related to this y. Then the mapping is onto. So let y belongs to r dash, and what is r dash? R dash is the set of even integers. So therefore y is even, and this implies y is even integer, and every even integer can be written as 2 times an integer x. And what is x? X is integer, x belongs to r in this, and therefore what this implies? This implies x is equal to y upon 2. From this, x is y upon 2. And now what is phi of x? You see, and phi of x is equal to phi of this y upon 2. And what is phi of y upon 2? By this definition it gets doubled. So this is 2 into y upon 2, and that is y. And thus we have obtained an inverse image of y under phi, which is x. So phi of x is equal to y. This shows this mapping is onto. Therefore phi is onto, and thus phi is a mapping defined like this. Is, we have proved, a homomorphism. Phi is homomorphism. It is 1 1 and it is onto. Therefore phi is 1 1 onto homomorphism, and thus the two ring phi becomes isomorphism, onto isomorphism, and the two rings, ring of integers and ring of even integers, though they does not contain the same elements, but they are isomorphic to each other. And thus this shows that thus R is isomorphic to R dash. These two rings are isomorphic to each other, and in that sense the isomorphism of rings is important. Now what is another property of isomorphism of ring? It maps 0 element to 0. See, we have R and this is R dash. 0 of this is mapped to 0 of R dash, and again the additive inverse is mapped to additive inverse under phi. That is, phi image of minus a is minus phi of a. And also an unit element in this is mapped to an unit element in R dash. And if R is commutative, then R dash is also commutative. Further, if R is an integral domain, then R dash is also integral domain. If these are isomorphic, the two rings are isomorphic. If R is a field, then R dash is also a field. So therefore the two rings are isomorphic, then these properties are preserved. Now there is an unit element in the earlier example we have considered, unit element in R dash, and we can claim that 2 is the unit element. 2 is the unit element in R dash. Actually this one under our mapping, A is mapped to 2A. So therefore 1 is mapped to 2. 2 is the unit element of R dash, because if you consider y in R dash, then what about y into 2? That is multiplication. Then y into 2 or 2 into y is by definition of multiplication. We have defined like this: y into 2, that is usual multiplication divided by 2, and which is again y. Also 2 into y, 2 star y. The multiplication in r dash is star. 2 star y is 2y divided by 2 is equal to y, and this shows that 2 is the unit element. So this is an example of isomorphism. So I hope you can understand this mapping, which is a special mapping known as isomorphism, and we have seen an example of 2 rings which are isomorphic to each other. Remaining part we will continue in our next lecture. Thank you for watching the lecture.